as Frank so eloquently mentioned, my name is Daniel Vacanti. I honestly don't like to talk about myself too much, but for anybody who wants to know more, they can ask Frank later. Hopefully, he'll do a little bit better job of explaining who I am. For those of you who've been to my presentations before, I like to keep them extremely informal. I do have some time reserved at the end for questions, but as we go along, if anybody does have any questions, by all means, raise your hand or interrupt me somehow, and we'll get those questions answered. If it's not immediately relevant, then of course we'll wait till the end of the presentation. And like I said, I hope that there's enough time at the end. Although I guess I only have 40 minutes, so we might be screaming through this a little bit as well. So, okay, with that, let's get going. I want to start off with an apology, with actually a very sincere apology, because we are unfortunately going to be talking for the next 40 minutes about metrics. And does anybody have children? I don't have children. A lot of people tell me that talking to software teams about metrics is like getting your children to eat their vegetables or something like that. I don't have children. I have cats. Has anyone ever tried to give a cat medicine? Something like that? Yeah? This is really what it's like talking to software development teams about metrics. So hopefully, I'm hoping that I'm not going to get this reaction from you guys as we go through this. But how many people have seen this relationship before? Can anybody tell me what this relationship is called? The title of the presentation maybe gives it away. I heard it over here. Little's Law. So would anybody in the audience disagree that this is Little's Law? No? Nobody? One person. My hope by the end of this presentation is that you guys will figure out that this is not Little's Law. Well, but actually, probably more correctly, that this is not wholly Little's Law. There's a lot more to it than just this numerical representation. And I'm hoping that's what you guys will get from this whole presentation. So let's kind of get into this. The first thing I need to do, though, is do just a kind of a short segue for some history. Classical physicists had Isaac Newton with his F equals ma. Modern physicists had Einstein with his energy mass equivalence. We, in product development, have what's known as Little's Law. We have Dr. John Little to thank for his law. And it's that law that we're really going to be focusing on for the rest of this presentation. So what is this law? This obviously looks a little bit different than that first one that I just put up. But let's talk about this version right here, because for those of you who don't know, Little's Law was, the reason it's called Little's Law is because not that it was John Little that discovered this, it was because it was John Little who was the first one to provide a rigorous proof of this relationship. And he provided that proof in 1961. This relationship had been known, this relationship in queuing theory had been known for many years before Dr. Little actually set down a proof of it. But this is the original statement of Little's Law. And what this is saying here is L represents the average number of items in a system, and L is related to a couple of other measurements in queuing in a queue, namely one, W, which is the waiting time, the average waiting time of an item in the system, and lambda being the average arrival time. Now, what I want you to take away from this is when Little's Law was first written, when Little's Law was first discovered, I shouldn't say discovered, when it was first proved, it was stated in terms of arrivals. Now, this is going to be a key point for us later, that when Little's Law was first discovered, or first written down, it was stated in terms of arrivals. And the reason that this whole law in general was important is because, as anybody who attended Don Reinertson's talk this morning knows, that it is very general, and it's actually very surprising about what little you need to know about your queuing system in order for this law to hold. Now, all three of these measurements are probably extremely interesting to a manager, to some type of manager that's managing a queuing system. The thing is, what's nice about Little's Law is it tells us that these three measurements behave and are bound by a very specific relationship. So while all three of these measurements might be very interesting to a manager, in certain contexts, you've probably only got two of these things. You're probably only able to measure two of them. And measuring the third one is actually very, very hard, if not impossible. And so that's why this law is extremely important, is because it says if you have any two of these things, you can get the third, regardless of domain, regardless of arrival processes, regardless of all kinds of things. Now, believe it or not, this relationship might seem fairly intuitive to you, but believe it or not, it's actually an extremely remarkable result. So the first question, I hope the first question that you guys might ask is, well, what assumptions about our queuing system do we really need to have in place in order for this to hold? And as I mentioned before, there's actually very, very few things that you need to have in place when you're stating Little's law in terms of arrival. And probably most people that you come across who talk about Little's law says these assumptions. One, that you have to have some notion of a stable system. Little is actually very specific about what he means by a stable system. It means that your underlying stochastic process has to be stationary. If anybody wants to learn more about stationary stochastic processes, I'll be the one hiding behind Don Reinertson when you have that question. One assumption is that it has to be a stable system. The next assumption is that you have to have long-running averages, and then the third one is consistent units. Now, when I talk about Little's law, I almost never, in fact, I might even go out on a limb and say that I never state Little's law in terms of these assumptions, stable system and long-running average. And we're going to talk about why I never state them in terms of these assumptions in just a little bit. All right. So let's go over just a very, very quick example. I know this seems fairly simple, but let's go over a quick example. It turns out, I think that Dr. John Little was a drunk, just like me, and one of the very best examples that he gives to demonstrate Little's law is the case of a wine rack. And let's say you have a wine rack and you want to know what the average age is of the wine in your wine rack. And let's say that on average, over some long period of time, you have 50 items in that wine rack. And let's say that on average, over time, you are replenishing that wine rack at 2 bottles per week. Well, Little's law would say that we can know exactly what the average age of the wine, of the average bottle in our wine rack is, and of course somebody can probably give it to me if we know this. The average age is, I have 50 items in my wine rack and I'm replenishing it with 2 items per week. The average age would be, I thought this was simple, maybe it's not. 25, right? 25 weeks. The average age of the bottle of wine in my wine rack is 25 weeks. And we know this exactly without taking any accurate information about when did a particular bottle of wine enter the rack and when did a particular bottle of wine exit the rack. Don't need to take that measurement at all. By knowing the long-term average is 50 items and by knowing that the long-term arrival rate of wine into my rack, I know that the average age of wine in my wine rack is 25 weeks. Does that make sense? Because that seemed to have stumped a couple of you. No? Okay. But wait. So all this was going on in the early 1960s. In the kind of the mid 80s to early 90s, operations managers came along and they said, you know what? This relationship looks a lot like our world. But in our world, L is work in progress. And in our world, W is something called lead time. And in our world, this lambda is something that we would actually call throughput, right? And they come along and they state Little's law in terms of work in progress, throughput, and lead time. A lot of you probably, let me actually, where work in progress, again, we're still talking in terms of averages, by the way. We're still talking in terms of averages here. Work in progress, this WIP, is the average work in progress in the system. This lead time is the average lead time of items in the system. And this TH is the average throughput, or the departure rate of a system. By the way, Dr. Little does a really good job, I think, of defining really what it means for something to be, to call something lead time. There's a lot of debate in our community about what lead time is and what cycle time is, and et cetera, et cetera. For the purposes of Little's law, he defines lead time and he actually calls it flow time, And what we're talking about is the amount of time that an item spends as work in progress, the amount of time that we count it as work in progress. That's what he's defining as lead time. And to me, which is generally in general agreement to how we talk about lead time, but to me that's a great way of thinking about it. So operations managers come along and they say, we want to state, instead of stating it in terms of wait time and arrivals, we want to state it in terms of lead time and throughput. And actually, this gets us closer to the form that you guys saw at the beginning of this presentation, where lead time equals work in progress over throughput. If we just do some very quick algebra, lead time equals work in progress over throughput. So we have now defined this specifically in terms of averages. Average lead time equals average work in progress over average throughput. Now, would anybody say that this, I put a little bit more detail around this, would anybody say that this is Little's Law? Now we're talking about averages within the system. You guys are a little bit shy. You're not going to say now, right? You're good. So, thank you, Dominica. Dominica's going to say that this is Little's Law. Well, we're still not quite there yet. Right? Because the question is, by defining Little's Law in terms of departures versus arrivals, is there something about the underlying assumptions that have to change? Because now we're talking about departures from the system. We're not talking about arrivals into the system. Is there something that has to change about the underlying assumptions for Little's Law when stated in this form? As well as, so far I've been talking about using Little's Law looking backward, right? If we get to the end of a specific period of time and we look backward, assuming some assumptions have been met, Little's Law holds exactly. What about if we look forward? Most people would argue the true value of a law is being able to make predictions from it, right? I know this relationship. Can I predict the future, right? F equals ma equal E equals mc squared. Can I start making predictions about our system using Little's Law? Well, the answer to both of those questions actually comes from a closer inspection of the true assumptions that really make Little's Law tick, that really make Little's Law work, right? And so, to be clear, I want to make sure for the next several slides, what I'm talking about when I talk about Little's Law's assumptions, I'm talking about Little's Law when it's stated in terms of departures, right? In that second form that we just talked about, when it's stated in terms of departures. And I'm also going to be talking about Little's Law when there is continuous work in progress throughout the interval of calculation. Turns out that there's some special cases and some fancy things that happen if your WIP goes to 0 over that calculation. So I don't want to go there. If anybody wants to know more about that, we can maybe talk about that at the end of this presentation, or you can come find me. But for the purposes of these next slides, we're talking about departures and we're talking about continuous work in progress. Right? Okay. So the first thing that we need for Little's Law to hold is this idea of consistent units. And while this seems probably obvious, you'd be surprised how many people screw this up. Right? A lot of teams I work with think that I can calculate throughput in terms of weeks, but then I'll get a calculation of lead time in days. It doesn't work that way. If I want to know lead time in days, I need to calculate my throughput in days. I also worked with one team that was trying to substitute velocity for throughput, and they were measuring their velocity in terms of story points over an iteration. That's what their velocity, and they plugged their velocity into this equation and thought that it was spitting out days, lead time in days. It doesn't work that way, right? If we want lead time in days, we need to measure throughput in days. If we're measuring throughput in weeks, we're going to get a lead time in weeks, right? So very, 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 very simple concept. We need to be talking about consistent units. Should be pretty obvious, right? But, yeah. So the next thing that we need is some notion of what Dr. Little calls conservation of flow. And there are two parts of conservation of flow. And the first part of conservation of flow is that all work that enters the system must flow through to completion and exit the system. Right? When you get these cases where work enters the system, it flows through halfway and then gets kicked out, if that is your world, you do not have a world that we can apply Little's Law to. Right? And my guess is a lot of you probably operate in that world. How many times does that happen where you start something, somebody comes along and says, that's stupid, why the heck are you working on it, kick it out of the system and start something else. Whether or not that's the right thing to do, that's not what I'm talking about, whether it's the right thing to do or not. If that is your world, you cannot apply Little's Law. The second, and I would argue more important, although maybe I wouldn't argue very hard, about conservation of flow, is that the average arrival rate of your system must roughly equal the average departure rate. And it's probably easier to demonstrate that in terms of a cumulative flow diagram. Now, you guys are probably, those of you who've been to a lot of sessions are probably sick to death of seeing cumulative flow diagrams, so I'm going to fly through this part right here. But just as a quick refresher, if this is a cumulative flow diagram, the slope of this bottom line is what represents the average departure rate or the average throughput of our system. And the slope of this top line is what represents the average arrival rate. So the slope of the top line is how fast stuff is coming into the system. The slope of the bottom line is how fast stuff is going out, right, very quickly. So let's look at a cumulative flow diagram in terms of just those two lines. And let's say that I have an average departure rate or an average completion rate that looks something like that. And let's further say that I have an average arrival rate that looks something like this, right? Well, a lot of you guys have probably been to enough presentations so far over the past couple of days that you know that the difference between those two lines at any point along those curves is our total work in progress. And that measured horizontally, the difference between those two lines is our approximate average lead time. Now, I'm going to give you guys some homework after this presentation. Do they have the concept of homework in Austria? Gentlemen, you guys know homework, right? I'm going to give you guys some homework. Whenever you see a cumulative flow diagram that's thrown up like this, and you see a horizontal line like that, and they say that that horizontal line is exactly lead time, your homework is to go up and slap the presenter, right? Because that is absolutely not true. Without knowing the underlying assumptions or the context with which this cumulative flow diagram was created, the best thing that we can absolutely say about this horizontal line is that it is an approximate average lead time. And I would argue in this context, that approximation is actually not very good. So this horizontal line is an approximate average lead time. So a lot of people would tell you, by looking at a cumulative flow diagram, this is Little's law in action. Because look what happens earlier on in this process. Our work in progress is much less. Our approximate average lead time is much less. And so what we get is Little's law, because you can see as work in progress goes up, lead time goes up. Right? And a lot of people use this as a justification for all things lean and all things Kanban, because they say Little's law is this wonderful, magical thing that says all you need to do is reduce work in progress and wonderful things will happen to your lead time. And oh, by the way, look at my pretty cumulative flow diagram that demonstrates that. The problem is, from a Little's law perspective, is we do not have conservation of flow in this. While Little's law might give you some insight about, yes, there is some relationship between lead time and work in progress, if we want an exact calculation using Little's law, we cannot use this picture. What we really need in terms of conservation of flow is something like this. If our average throughput is that, then we want our average arrival rate to be something more like that, so that our WIP and our approximate average lead time remain essentially constant or predictable over time. When I talk about predictability, when I talk about driving predictability into Kanban systems or just systems in general, this is what I'm talking about. This is conservation of flow. Average arrival rate roughly equals our average departure rate. Right? But wait, there's more. So remember that whole thing about stable system. Remember I said I almost never talk about Little's law or assumptions for Little's law in terms of a stable system. Because that's what happens. When somebody's talking about Little's law, and people who should know better, you go up to them and say, well, what are some of the assumptions that need to be in place in order for Little's law to hold? They'll kind of clear their throat and they'll kind of wave their arms and they'll maybe say something about you need to have a stable system, and then they'll quickly run away. They'll probably quickly go run behind Don Reinertsen, which is exactly like what I would do. The reason that I almost never talk about Little's law in terms of a stable system is because Little gives us very precise language around what it means to have a stable system. And just like there were two parts to conservation of flow, there were two parts to this idea of stable system, of having a stable system. So before I get into that, let me throw this diagram up. This is a cumulative flow diagram, and it looks like we have roughly some pretty good conservation of flow going on here. Would anybody say that this picture is a stable system, is a picture of a stable system? So I've got an answer of yes. Anybody? Good enough. Pretty good answer. Anyone else? The answer is we don't know. We do not have enough information to know whether this is a stable system or not. And the reason that we don't have enough information is because there's, like I said, there's two exact parts to a stable system, right? And the first thing is that the average work in progress must be at the beginning of the calculation, must be roughly equal to the average work in progress that is in the system at the end of the calculation. Now, if we go back to this diagram, looks like that's exactly right. I mean, if we were to do a Little's Law calculation here and a Little's Law calculation here, we have roughly the same work in progress at the beginning and at the end. So in terms of system stability, okay, that's a check. That looks pretty good. The problem comes in the next one, the next part of system stability. And the next part of system stability is that the average age of your work in progress must neither be increasing nor decreasing over the life of the calculation, right? So when you're looking backward, if your work in progress was aging, or if it was getting shorter, then Little's Law does not apply. Can anybody think of a particular queuing method or queuing approach that this might suggest we need to use for Little's Law? If we don't want our work in progress to either artificially age or unartificially age, what are some approaches that we might take? Yeah. Maybe, yeah. Something like a FIFO might, yeah, something. But I mean, maybe I don't want to suggest that FIFO is the only one. Round robin might work, right? The interesting thing, though, and I want to make this very, very clear, is that Little's Law does not prescribe a specific queuing approach. Right? It doesn't matter what queuing approach you take, as long as the average age of your work in progress does not increase or decrease over the life of the calculation. Now, those of you who've seen me do presentations before know that I like to go on a rant about class of service, and I won't spend a whole bunch of time talking about this right now. But one of the biggest reasons why I don't like class of service is because when teams introduce class of service, what they're doing is they are artificially affecting the average age of their work in progress without really knowing what they're doing. And by doing that, I would argue that because they don't know what they're doing, they're introducing more unpredictability into their system rather than reducing that unpredictability, making their system more predictable. And having an understanding of Little's Law would give you some of those insights. So, going back to this picture, can we say with any certainty that this system is stable, given what I've just showed? So, average age of work in progress has to be roughly the same at the beginning and the end, and the average size of our work in progress must be the same at the beginning and the end. Can we say that this system is stable? Good enough. Yeah, so the answer is we can't. Just by looking at this cumulative flow diagram alone, we have no idea of system stability. This is one of the reasons why I do not like to talk about Little's Law in terms of system stability, because Little actually gives us the blueprint. It gives us the rules that we need in terms of system stability. Right? Okay. All of this is leading to finally our definition of Little's Law. So yes, average lead time equals average work in progress over average throughput, assuming for the time interval of the calculation, you have all of these things. Right? The measurement units are consistent, that the arrival rate roughly equals the departure rate, that all work that enters the system flows through to completion and finishes, that the average age of work in progress is not increasing or decreasing, and that the average size of a work in progress is not increasing or decreasing. Right? This is now Little's Law. If you have this relationship with all 5 of these things, now you have Little's Law. If you have this relationship with 3 of these things, you just have this relationship. You don't really have anything. It's not really this relationship, this numerical relationship is really not telling you anything. Okay. Like most things in this world, I think what's really interesting about Little's Law is what it doesn't say. It's not what it does say, but what it doesn't say. Notice that I haven't said anything about the size of the items that are flowing through as work in progress. A lot of people will tell you that for Little's Law to work, you have to have the size of your work in progress, or the items of your work in progress, to be roughly equal. Absolutely not true. That's probably the second part of your homework. If anybody ever says that, you get to go up and slap them, right? Because that is absolutely not true, right? That the distribution underlying the arrival or departure rate That Little's law prescribes a specific distribution of that underlying arrival departure rate. Absolutely not true. You can have whatever arrival rate you want, whatever departure rate you want, whatever distribution of those things. Little's law does not prescribe that. And Don Reinerson actually did a better job of talking about all this than I do, as he normally does. It doesn't talk about how many particular people are working on an item. It doesn't talk about the order in which you're working on these things. There's all kinds of things that you don't actually need to know in order for Little's law to work. Right? It's one of the reasons that makes it extremely, extremely valuable. It makes it extremely, extremely powerful. Right? Even though it's powerful, it's not omnipotent. Okay? And so this is where we get to the so what. Does anybody know who Russell Healy is? Russell Healy is the guy who developed the Get Kanban game. When Russell Healy comes to my presentations, he usually raises his hand about halfway through and he says, so what? Right, so now I make sure that I have a Russell Healy slide in my presentations that say, okay, so what? Why have I gone on for, I don't know, how long have I gone on for? 25 minutes talking about Little's law, so what? The so what is, when teams are starting out, by having an understanding of Little's law, and I'm not talking about that numerical relationship, I'm talking about the assumptions behind it, right? As I mentioned before, that actually gives us a blueprint for some very specific process policies that we can put in place in order to drive predictability into our system. Whether we're actually going to apply Little's law or not is almost beside the point. In fact, I like to talk about Little's law. Most people will talk about Little's law as a justification for doing Kanban. I would argue that Kanban is a justification to apply Little's law. It's a slightly different way of looking at it. So by understanding these assumptions, it actually gives us insight into certain policies that we should be introducing right away in order to drive predictability into our system. Does this mean that this is going to be the final end state of our system design? Absolutely not. But when you're starting out with Kanban and you're working with teams that are starting to work with Kanban, I would say look to Little's law, and especially the assumptions behind Little's law, in order to drive some policies that you guys should be putting in place to drive predictability. Things like, hey, we want our average arrival rate to roughly equal our average departure rate. We want those two lines in our cumulative flow diagram to be roughly equal. We don't want our work in progress to be artificially aging, or we don't want to be shortcutting things in our work in progress so that they are average. What's the opposite of aging? I don't know, faster completing or something, I don't know. Things like that. Those are sample policies that we're going to want to put in place. This is a guide, like I said, a guide or a blueprint of policies that we can put in place for our system. Okay? I want to say just a quick word about predictability, too. Predictability in my world does not mean deterministic. So remember I talked about before, the power, a lot of times people say the power of a law is can we make predictions with it? And with Little's law, the jury's kind of out in terms of whether we can really make predictions with it. If we have all of those 5 assumptions in our system, and if those 5 things don't change over time, then we can probably be fairly reasonably confident in our ability to make predictions. But what I'm not saying is that we can absolutely deterministically determine the future, right? That's not what I'm talking about, right? The second thing that I want to caution you guys on is Little's law works, but it's still an average. Right? Even if we were able to predict the future, what we would be predicting is an average future. And in most of our worlds, average is not good enough. What I would say, though, is by putting in policies that align to these assumptions, we're now pulling ourselves back into our world where average might be good enough. It probably still isn't, but it's going to be a lot closer. That average is going to be a lot closer to good enough. So those are some things that I wanted to say about determinism and predictability. So if you want to learn more about this stuff, this presentation will be made available to you guys, so you don't have to write down these links. But if you want to learn more about this stuff, there's a great paper out there written by, of course, Dr. John Little. Don't worry about this URL. If you just Google Little's Law Chapter 5, it should be the first result that comes up. So Little's Law Chapter 5 is a paper he co-wrote with a guy named Dr. Stephen Graves that outlines everything essentially that I talked about here. Frank Vega, who introduced me, has written several blog posts about Little's Law that contain some very, very interesting things as well as, and this is, of course, you guys knew there was going to be a shameless plug in this talk, is Frank and I are teaching a Kanban metrics class. Tomorrow it is, right after this conference, we're teaching an all-day Kanban metrics class. So anybody who wants to learn more about this stuff and really what goes on beneath this, there is that class that is available. So if you guys want, if you want to sign up for that, just come find me or Frank, and we'll get you figured out with that. So with that, I hope I have left myself enough time for questions. Are there any questions?
So the kind of the assumption in the lean community, at least, is that little snow is good enough to begin with. So by just using that as a way of looking at how you can improve the system, and because most of the problems in the system is usually wait time, it doesn't really matter if the calculation holds true. Mm-hmm. And if we really look into queuing 3 area, I think little slow only holds for like the M1 queue or something like that.
No, actually, it holds independent of your queuing system. But I want to address. Sorry, did you finish your?
So kind of the point is, it's good enough to get started. Yeah. You have such a long journey to get to the place where a true formula would actually give you the extra benefit. Right. Would you agree?
I would agree that limiting work in progress somehow when you're starting out is a good thing to do. What I probably wouldn't agree with is using Little's Law as a justification as why you should limit work in progress, because I would argue that it's really kind of coincidental that in our world, limiting work in progress produces better average lead times. And the reason I would say that is because in our world, the arrival rate, that first cumulative flow diagram I show, in our world, it's almost always that the arrival rate into our system is always going to be much, 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 much greater than our departure rate. We always have more stuff to work on than we have resources to work on it, right? And so in that world, any type of limiting work in progress is going to have positive results. Little's Law or anything else being given as the justification for that. So what I have a problem with is when people say that we can deterministically use Little's Law to say that X amount of reduction in work in progress is going to lead to X amount reduction in lead time. And that's, I think, where people fall down using Little's Law in terms of trying to make these forecasts and these predictions about the future. Because what Little's Law says is looking backward, if I get to the end of a time interval and I look backward, assuming all these assumptions, Little's Law is exact. Looking forward, however, let's say when I was looking backward, I got a lead time calculation that, doesn't work for me. It's 10 days and I need it to be 5. And so they'll plug into Little's Law and say, Little's Law means that, well, okay, to get my lead time down from 10 to 5, I needed to reduce my work in progress from 20 to 10, right? What Little's Law does not say is by making that change in work in progress, it's not going to change the other two variables. It makes no predictions about changing your work in progress could have a positive or negative effect on changing your throughput, which could have a positive or negative effect about your change in lead time. That's where I have a problem of people applying Little's Law in terms of making those predictions. So I don't know if I've answered your question or not, but. I would say following those assumptions behind Little's Law is by all means, yes, good enough in order to get going. Like I said, it's not the end state, but yes, I would agree, yes. This is absolutely, and this is one of the reasons why I'm giving this talk, is because I think by understanding these assumptions, that is a good enough place to start. And I think it's a really, really easy, low bar to get over in terms of driving predictability.
Any other questions?
No, not Yuval. Don't let Yuval ask a question. No, I said no. No.
More like a comment, I think. Taking Don's comments about reducing WIP by 20% after you're 2 times above the average, I think what you can see there is that the throughput will go down, or the effectiveness of your system might go down, and that might be the reason that Little's Law might not predict what will happen. Because, for example, you don't have enough versatility for people to swarm more effectively to the work. The transaction costs will be something that will affect you. So you might find problems. You'll need to deal with them in order to get back to good throughput, and then you might see the reduction in cycle times. That's at least my understanding. What do you think?
Okay, we have time for at least one or two more questions.
Probably one more. Yeah.
So you talked about class of service and class of service invalidating Little's law. I kind of understand why, but also kind of wrestling with class of service was also designed to increase predictability.
Yeah.
But then do you apply Little's law per class of service? Does that make it work again?
Right. Okay, yeah, so the first part of your question was that I think you said that I said that class of service invalidates an assumption behind Little's law. I want to be clear, if I said that, I misspoke. What I meant to say is that class of service in and of itself does not violate Little's law. Little's law says nothing about the order in which you pull stuff through the system. It says absolutely nothing about that. What I did say, though, is that most people, when they go and read David's book and they implement class of service, the way that they implement class of service violates Little's law, and they don't know that they're doing it. And so then the second part of that would be, you said that class of service is supposed to introduce more predictability, and I would argue because people don't understand really why they should be implementing class of service and how they're implementing class of service, I would argue most of the time class of service introduces more unpredictability than predictability. The only predictability you get is for those items with a higher class of service. You get actually a ton more unpredictability for those stuff that have less class of service. Now, by using Little's law as a guide, though, I'm sure, I haven't done it yet, but I'm sure that there are class of service schemes that you can come up with that would still follow Little's law and would still give you predictability across the whole spectrum. Now, I think to get to your third part, because I think there was a third question, is could we apply Little's law to each class of service? And the answer to that, I think, would be yes, we could, again, assuming that we're following these assumptions. If we're constantly pulling people off of lower class of service to go work on higher class of service stuff, then that lower class of service stuff would now start to artificially age, right? And now Little's law would not apply in that world. Make sense? I did a lot of hand waving. That's what I do. I pace and I flail when I talk. So I hope that made sense.
Has there been any work done on, because we talk about averages. Averages they could be reasonably useless if they're averages of certain distributions.
Yes.
Is there any work done in the real world to see what these distributions look like?
Oh, what the actual distributions? The only work that I've seen in terms of studying distributions, I know Frank has published some stuff on distributions. I know Larry, how do you say Larry's last name at Raleigh? Mascheroni. Larry Mascheroni at Raleigh has published, I think, some work on some of those distributions. I mean, that's where I would go. I don't know if Don has anything to say about the underlying distributions as well. So certainly I would argue that by understanding what those underlying distributions are, that would probably be the next step that we can take. After we get this Little's law stuff mastered, the next step that we would take is by looking, I think, a little bit more seriously about those underlying distributions, potentially. But that is probably so far down the road. I would say that's not, if you're starting out, that's nothing you really want to concern yourself with until we've mastered some of this stuff. Did you want to say something to that? Sorry? Oh, yeah, so when's your talk? Because Kirk will talk about that.
So I'm going to talk a little bit about distributions in my talk straight after this one.
Or Carl. Sorry, I said Kirk. Carl Scotland will be talking about that. I think that's just about it. So the point of the presentation, understanding the assumptions behind Little's law is probably going to get you a lot further down the road in terms of predictability rather than just blindly applying Little's law in a deterministic fashion. So thanks everybody for coming. Thanks very much for your attention, and thanks for the questions. Thanks.
Thanks, Dan.